So I'm going to talk about, as I said, the reactive force field method. Also, in the end of my presentation, I'll talk about a sort of a recent extension of reactive with some sort of explicit electrons. And here's the picture down below that belongs to that. That's the so-called e-ReaxFF method that essentially enhances the reactive tool with a limited amount of explicit electrons. And I'll get back to that towards the end of my presentation. In the meantime, I'll be focusing quite strongly on recent application of 2D materials, but also provide a more general overview of the reactive force field method. And so there's a number of people from my research group that have participated in it, and I'll acknowledge them as they come along. They're also, their names are here in my first slide. Another role, apart from my research group that I play at Penn State, is I'm the director of the Material Computation Center. That is one of the 4 laboratories within the Materials Research Institute at Penn State. And that is arguably one of the highest ranked material institutes in the United States at this moment in time. And we try within MCC to really integrate computational chemical tools more actively with experimental operations. So the common procedure is still that experimentalists find a new material or a new sort of procedure that works for them, and then the computational chemist comes along and kind of explain why it works. And that's clearly useful, because if you understand why it works, you can probably further improve the concept. But there's probably a better way that that computational chemistry can get included. That's much more at the beginning of a project, where we can use computational chemistry tools to very rapidly guide experimentalists towards potential top candidates for new material combinations. And a big advantage there of simulations is that simulations are relatively inexpensive. They're not for free, because computer time costs as well. But they're typically much less expensive than their experimental equivalents. And that allows you to test very much out-of-the-box concept. You can just say, okay, I draw across the periodic table, I try some elements there. If it turns out that the concept works, we can then go back to the experiment and see if we are willing to invest the resources to make that experiment happen. So really trying to have the theory lead experiments, trying then instead of the theory following the experiments. Another role I play is, 8 years ago, I founded a company called e-ReaxFF Consulting, and that was very much in response to the growing requests for reactive parameters, and that came from various sources. So reactive is integrated in open source code like LAMS and NanoHub, but also there's a number of commercial reactive providers. In particular, one company that we work very extensively with is SEM Amsterdam, who releases the AMS code. And that availability of software essentially led to increasing demand for reactive parameters, much more than my research group at Penn State could provide. So we started the company in 2013. That essentially provides consulting for force field development and also for advice on how to integrate reactive in molecular dynamics and Monte Carlo simulations. And so we now have completed over 25 projects. Main customers are industry, but we also have a number of academia clients, and I'll show one example of such a project in my presentation later down. Okay, so the concept is that in principle, clearly, we would love to use quantum mechanics for everything. Quantum mechanics is arguably the most fundamental tool to simulate a relationship at atomistic-scale level. But unfortunately, quantum mechanics is very, very expensive computationally. And so typically one only applies quantum mechanics for relatively small systems. And if you use, for example, a particular popular quantum mechanics-based tool, density functional theory, you typically limit your DFT to, let's say, a maximum of about 500 atoms. If you do something like molecular dynamics using DFT, so AMD, then you can have a couple of picoseconds, but that's pretty much the limit. So one step up from quantum mechanics is what we call force field methods. These essentially stop trying to solve Schrödinger equation and use a set of empirical relationships. That means that these empirical relationships have to be trained. They're not as transferable and typically not quite as accurate as quantum mechanics, but they're computationally much cheaper than quantum mechanics, and as such can be applied to much, much larger systems. And indeed, traditional force fields can now be applied to billions of atoms, and time scales going to approaching milliseconds these days. Now, if you want to do chemistry on top of that, then the demands that are being put upon a force field become much more stringent. And so you can still stay within quantum mechanics. You can do quantum-based molecular dynamics. That is becoming increasingly popular because our computational tools get better, our computation facilities get better, and also the algorithms behind it improve. But that's still arguably a very expensive method. Another option is to make quantum mechanics faster. So we go, for example, to semi-empirical methods, and a very popular method in that realm is what we call tight binding DFT. That is essentially indeed allows us to scale up DFT to something like thousands to 10,000 of atoms or so. A third option is to go the other way around. So instead of trying to make quantum mechanics faster, we essentially try to make force field methods more sophisticated and essentially allow them to make and break bonds during the simulation. And so this field was really initiated in the late 1990s by Tursov and Brenner. With the so-called Tursov and Brenner potentials, which for the first time indeed allowed connectivities to change during a simulation. And so this in the field is quite often called the first generation reactive force fields. And reactive is an example of a second generation reactive force field, where on top of the Brenner and Tursov potential, for example, didn't really include non-bonded interactions and didn't include charges. Many of the second generation reactive force fields like COMB, MEEM and all that have essentially the ability to do weak interactions and to include some level of Coulomb interactions as well. And now for the last couple of years, a fourth option has become available. That's essentially neural network-based potentials. How that we can essentially, instead of using a fixed set of functional forms, we essentially use a neural network as a much more flexible concept. And so the people have indeed been using neural network quite successfully for sort of binary, ternary type sort of materials. And so that's it will be very interesting to see over the coming years how the communication goes between the traditional sort of fixed physical type sort of concept of force field like reactive-F and these neural network based potentials. So reactive-F is just at the Brenner potential and the Tursov potentials are essentially a so-called bond order based potential, and so they assume that there is a continuous relationship between bond order and bond distance. This is a empirical relationship, and so in reactive-F, this is pretty much the equation that we use for there. You see there's a couple of parameters in there. There's also interatomic distance Rij, and what this equation simply does is it converts interatomic distance Rij to bond orders. And so in the top left here we have the example for carbon. So we see that around 1.5 we have a total bond order of roughly 1. And if you go to 1.3, the bond order goes to 2 until it essentially reaches total bond order of 3. And that includes agreement with our chemical intuition. And then we would still like to use some of those angular terms that have been very successful in non-reactive force fields. So we have these angle-dependent terms, we have the dihedral terms, but we make them all bond order dependent. So when a bond breaks, that all the free body and four body terms automatically smoothly go to 0 as well. On top of that, we have a full set of non-bonded interactions, van der Waals and Coulomb, both of them. And what's unique about reactive-F is that we calculate them between every atom pair. So even on a bond, we calculate the Coulomb interaction. That means that in reactive-F, the bond dissociation energy is a sum of the covalent part of the bond and essentially the ionic part of the bond. And that means that reactive-F can make a relatively straightforward transition between covalent materials and ionic materials. And so every step, also the charges are calculated using the electrostatic equilibration method by Mortier and co-workers. So that means that every step, essentially a fresh set of charges is calculated. These charges are polarizable and geometry dependent. And so this on the top right is kind of how reactive-F is organized. So the non-bonded section and the bonded section are pretty much separate from one another. So we calculate bond orders, they get corrected for over-coordination, we find angles and torsions, and we calculate the various energy contributions. At the same time, we do this we do independently the van der Waals and Coulomb interactions, and these get then added up to system energies and then associated forces. We can then get integrated in the regular molecular dynamics concept. So why we do this, reactive-F is not more accurate than quantum mechanics. When we train it well enough, we can approximate and get pretty close to DFT accuracy. But the main reason why we do this is it's significantly faster. So reactive-F is roughly 10 to the power 6 faster than DFT methods, and it scales better. Reactive-F scales almost linear, while most ab initio-based methods scale n to the power of 3 or worse. So if you double the amount of system, simulation time goes up by factor 8. reactive-F, if you double the system, simulation time goes up by roughly a factor 2. Now, one thing that's unique about reactive-F and that really distinguishes it from many other empirical reactive force fields is its focus. Its focus is very strongly on trying to get reaction barriers right. And so here's an example of that. One thing that reactive is quite good at is these reaction barriers for so-called bond order conserving reactions, where the total bond order in the transition state is roughly the same as in the reactant and the product. And here's an example of such a reaction. We have 4 water molecules on the left side. They react to 4 identical water molecules, just only reorganized, and they go for a transition state where essentially 4 bonds are getting made and 4 bonds are getting broken at the same time. So the total bond order is the same in the transition state because we have essentially half bond orders here. And what's unique about this reaction is very important for things like enzyme reaction. This is pretty much what enzymes do. They tease water molecules in the right configuration and then can break relatively strong bonds at a very low energy cost. Here, because this reaction is only a barrier of 20 kcal, and remember that each OH bond is worth about 125 kcal, so roughly 5 eV. And so we indeed can do this reaction at a fraction of the sum of the bond energies, only 20 kcal. So this is actually a reaction that can happen at room temperature. This is not only related to aqueous chemistry as an example from combustion. This is a so-called crop fragmentation, where a single step, a small biofuel molecule gets converted in water and formaldehyde. And the barrier of this is only 65 kcal. That is weaker than any of the individual bonds in the molecule, and that is because it essentially uses these bond order conservation concepts. This also works for catalysis. So here's an example of a reax simulation of methanol decomposition on platinum surface. And here the bond orders with the platinum surface can essentially weaken the bonds in the methanol, allowing us with relatively low energy to break bonds. And so we can compare reactive-F with quantum. So the red dots here are from quantum mechanics. And reactive-F can essentially reproduce the barriers reasonably well. And we can also look at competing reactions. A very important competing reaction is the dark gray curve over here. This is where we break the carbon-oxygen bonds. And that on platinum has a very high barrier. And that is why indeed platinum gets poisoned by carbon monoxide. And so we indeed have to mix platinum with other metals like ruthenium or nickel, so that we have hydroxyl groups available that can help in breaking the CO bond. But you see that all across the energy landscape, the reaction landscape, we actually get a pretty good agreement between reactive-F and DFT. So once again, we do this not to have a method that is more accurate than DFT. This is our goal is really speed and try to get as close as we can to DFT in training. Now remember that we don't have to necessarily train reactive-F against DFT. We can also use other ab initio methods. We can, for example, train reactive-F against copper cluster. But typically, the training sets are large enough that getting them all populated with copper cluster level accuracy is typically too time consuming. Now, an important point to make is that reactive-F is much faster than DFT, but it is relatively slow for a force field. So if you look at this graph here on the bottom right, this is from Aidan Thompson, one of the main developers behind LAMPS. You see, for example, that EEM is roughly 50 to 100 times faster than reactive-F. And that's not surprising because especially the charge calculation in reactive-F is relatively time consuming. So reactive-F got going in 2001. We developed it first for hydrocarbons. And then we found out that the concept of a polarizable charge concept on top of a bond order was actually highly transferable. So the bond orders work pretty well for metals, while the polarizable charges allows us to essentially transfer this concept also towards more ionic materials. And so we can indeed, for example, describe sodium chloride pretty well with reactive-F. In that case, all the bond orders or bond energies kind of switch themselves off, and everything pretty much becomes Coulomb-based. So all these force fields, so this periodic table shows you which particular elements we have visited in some shape or form with reactive-F. Bear in mind that this promises a bit more than we have. For example, we have a titanium oxide and a titanium carbide force field, but at this moment in time we don't have a titanium boride force field. So this image just shows which elements have been visited. It doesn't show the binaries and the ternaries that we have developed. We have been pretty active distributing the code. I personally distributed the code to probably over 3,000 research groups over the years, but also LAMPS, reactive-F is distributed through LAMPS. I don't control the distribution, so there's arguably even more research group that actively uses reactive-F. There are two good parallel implementations, LAMPS reactive-F and ADF reactive-F. Which is distributed through SEM Amsterdam. This provides, and in particular, ADF is very popular with my group, or they've now renamed themselves AMS. That provides a highly efficient and very user-friendly reactive-F simulation environment. So just a couple of examples of ReaX use and give you some idea how we typically these projects get formulated. reactive-F, one of the early applications was in combustion here on the top. And so we train reactive-F, for example, against all possible valence angles, angular combinations related to hydrocarbon combustion. So every combination of oxygen, carbon, and oxygen, we make a small molecule that has that angle in it. And at the DFT level, we then scan that bond, scan that angle, and train reactive-F against it. It's clearly non-reactive, but that's part of our training set. And then once the force field is ready, we pick a sort of a small system where we feel that we can validate the force field for. So in this case, we picked JP10. JP10 is a very highly strained hydrocarbon that is used for high-flying aircraft because it provides a very, very large amount of energy. And so we performed a pyrolysis simulation. We saw here, these dots over here are the ReaX result at roughly 2000 Kelvin. And we could directly compare them against experiment. Experiments were done around 1000 Kelvin, but we see we're pretty much on the same line and we can get an effective activation energy. Note that JP10 was not in the ReaX training set, so we were very happy with this level of agreement. And then we can expand the complexity, for example, at the catalyst. In this case, we had a pyrite chromia catalyst, where we look at how the catalyst essentially ages during exposure to the butane and how pyrite deposits itself on the chromia surface. For materials, we quite often train against these type of equations of state data. This is an example for titanium dioxide, where we have rutile, anatase, and brookite. They are roughly equivalent in energy. So we can essentially train against these energy volume equations of state, which you can derive from DFT. And in this case, we did a direct reactive-F versus ab initio MD comparison. We took this small system and simulated how fast water would dissociate in the system at both the ReaX level and the AMD level, and we found pretty good agreement. And after that, we scaled this up. This is roughly about 650,000 atoms. This was run with LAMPS by Murali Raju, a past grad student in my group, where we essentially showed how water is essential for the oriented attachment of these clusters. A very attractive application for reactive-F is the connecting strain to chemistry. So here's an example where we developed reactive-F for hydrolysis in silica. And then we used this small nanocluster that is highly strained on the top, and it's very low strained on these sides. And we put them in supercritical water, and we see that all the hydrolysis reaction indeed are localized at a high strain domain. So there's a very strong sort of correlation between strain and chemical reactions there. And this was later scaled up by Pittman and co-workers. They were working at IBM, who essentially used LAMPS to run this very large-scale simulation on the clay zeolite interface, where we see water dissociation, but also we see essentially physical non-reactive transfer of water. So we see both reactive and non-reactive diffusion of water. Reactive-F is quite popular in the high energy community, so pretty much explosives and other types of propellant type sort of information. So it can be quite successfully trained against various reaction channels. This is, for example, the RDX dissociation channel. We can then do small scale tests for sort of physical effects, like things like shock speed in the crystal, and also things like shooting tendencies. This is essentially a ReaX result for TETB initiation, where we see all these sort of soot molecules getting formed. And this is work from the group from the University of Southern California, Priya and Nomura and co-workers, where they use, this is roughly 4 million atoms or so, where you send a shock through a high energy crystal with a defect on it. And we see indeed that near the defect, we get a very high temperature increase that then triggers the chemistry. So we see a conversion of shock to essentially initiation chemistry. Batteries have been a very popular topic for ReAx, especially, well, as I said before, strain related chemistry is very important in batteries because batteries undergo enormous volume changes during charge-discharge cycles. And we indeed see here that we have, for example, if you take a lithium nanotube system, at low strain, nothing happens. But if you put strain on the system, we see that the lithium can eat its way right through the nanotube. So very much the strain kind of makes the lithium far more reactive towards the anode material. And so this is now something that you can with reactive do for realistic anode materials, where you can use, for example, this type of carbon onion anode, and we can simulate the lithium is in green here. We can simulate the physical diffusion, but also can see how the carbon network rearranges itself during charge-discharge cycles. So finally, and this is a topic I'll talk a bit more about in my next couple of slides, reactive over the last 5 to 6 years has been extensively used for 2D materials. I'll talk a bit about chalcogenides, molybdenum disulfide in my next slides. But also, I won't talk too much about these, but MXenes has been a very significant target for reactive simulations, especially things like MXene interfaces with electrolytes, where we look at the reactions of the electrolyte with the MXene surface and how that reactions essentially controls the diffusion of things like electrolytes through the MXenes. Graphene has been also a very popular target, and then with reactive we can expose, for example, these 2D materials to extreme environments. This is an example of something that you might see in satellites and spacecraft, where this is a silica particle hitting a graphene surface at a speed of about 5 to 10 kilometers a second. So that's not the speed that you will see very often on the sort of earthly environment, but in low Earth orbit, this is a pretty common speed. And we see indeed that this creates significant amount of damage to the graphene, and we can see how this damage propagates. We also see how the shock wave kind of propagates ahead of the defect. I won't talk too much about this, but in general, so there's been a lot of activity also about speeding up reactive-F. Essentially, so reactive-F by itself can get you to probably nanoseconds, maybe 10 nanoseconds. If you really pool all your resources, you can get yourself to 100 nanoseconds. But on top of that, we can use a wider range of acceleration tools. A very popular one is things like parallel replica dynamics. If you have an isolated low probability event that kind of drives your chemistry, parallel replica dynamics is a very good way to sample these things, and essentially you can parallelize time if you use it right. Parallel temperature is quite attractive. Then you essentially run the same simulation as a bunch of temperatures, and you swap between these temperature images. That was used by Atmani co-workers to turn cellulose into graphite quite well. But also, in this case, the energy landscape essentially remains unaltered. What you also can do is change energy landscape and essentially make the transition state more accessible. So that's what you do in bond boost type sort of simulations. Another option is to combine Monte Carlo with molecular dynamics, and especially forced bias Monte Carlo has turned out to be very efficient in simulating long-term crystallization, where you really can get yourself to microsecond, maybe even milliseconds of time, and look at these more complex crystallization patterns. My group for polymers has developed a so-called tracking option, where we can recognize a pre-transition state and kind of push it across the transition state. This is very useful for polymerization. And in general, there's been some attempts at making reactive-F run on GPUs, and that worked out reasonably well, especially in reactive-F, for example, using the LAMPS COCOS, can give you typically the equivalent of 40 CPUs for a single GPU. And in general, this allows you access to a kind of microsecond timescales and effectively running reactive-F at almost non-reactive force field speeds. So here's an example of such an accelerated dynamic. I show you this image. So this is a nice example of how we can use force bias Monte Carlo to accelerate the chemistry of here carbon nanotube growth. With regular molecular dynamics, you can maybe get yourself to stage E. Because that is pretty much where you are after about 10 to 50 nanoseconds. So you still begin to see a bit of a graphene cap. but it's very hard to get beyond that. But with a combination of Monte Carlo, you can so where you take the Monte Carlo steps in the direction of the forces indicated by molecular dynamics, you actually can grow very, very high quality crystal structures, but still do that at a relatively affordable time. And you can then do fancy things like you can use, for example, how electric fields affect the growth, and how, for example, cobalt, bipent, argon can essentially change your, can bias you between 5-membered ring growth and 6-membered ring growth. Okay, let me go back to some research, recent work on 2D materials. This was some work from Aditya Lele. He got his PhD from my group last year. And so one of the projects he worked on was the growth of 2D boron nitrides. This is typically done, one of the ways to synthesize these materials is use chemical vapor deposition, where you use feedstock like NH3 and B2H6, you heat them up, and if you get the right conditions, you can then grow some boron nitride sheets out of those. So we wanted to simulate this, but one of the problems that we had was that we didn't really know what the chemistry was. I mean, the initial chemistry you could have a pretty good guess at, but we didn't really know what the sort of the secondary chemistry was. So what we did was a method that's pretty popular in the neural network community, is that we say, okay, we have a couple of basic reactions that first train reactive against those. And then with that force field, we do then simulations. If we at elevated temperature, we see some new clusters formations. And if they're indeed not new, then we can do some DFT on them and add them back in the training set. So we have kind of a self-consistent force field development concept. And in a couple of cycles, we get a force field that properly trains against these things pretty well. So we can train these things before parameterization with a couple of very significant outliers. After training, we see a reasonably good agreement between the DFT reaction energy data and reactive-FF. And so we are ready to actually use this force field. And so we can do these type of simulations. These are actually pretty cheap simulations. This takes typically only a couple of hours on a couple of processors. So we can load, for example, look at precursor effects. We can load up an HBNH precursor or a BM precursor. And we see indeed that these produce very different structures. The BM precursor is much more reactive than the HBM precursor, but the HBM precursor essentially provides more high quality two-dimensional regimes, while the BM precursor leads to much more curved type sort of structures. And so we can then, based on that, we can come up with sort of quality assessments. And you can, so we can, for example, count the amount of 6-membered rings, but we also can figure out, how well connected are those 6-membered rings, where we say that ring number 3, 4, and 6 are well connected. So these are what we call high quality growth. Well, ring number 4, it only has one neighbor, and so that would be essentially a lower quality concept. And so with these type of quality concepts, you can then figure out indeed what is, for example, a preferential growth temperature. And we see here that indeed at 50, this guy, we find that at 2000 Kelvin is roughly the optimal growth temperature. If we go beyond that, we still get a lot of 6-membered rings, but they're all kind of badly connected. So we get isolated 6-membered rings that don't grow into sheets. And so if you want to grow a decent quality boron nitride, there's clearly an optimal temperature, and we can develop these things pretty quickly using these molecular dynamic simulations. Now, one step further, so this was how my company got involved. So this, we got contacted by Bin Louis. He is working at Kansas State University, and he wanted us to combine a boron nitride force field with a nickel chromium catalyst to see if we actually can simulate the 2D growth of these boron nitride on these metal substrates. So my company developed that force field, and then the group from Bin Louis did essentially the MD simulations, and they managed to connect these reasonably well to experimental observations. So that led to 2 publications, and we can get very nice sort of history about how these 2D material grows, what are the initial precursors, and what sort of decisions the material makes along the growth axis. Other materials that we've been working on recently, we've gotten very involved with Josh Robinson's group at Penn State, who tries to synthesize 2D metals based on gallium. And so with reactive-FF, we could essentially, these are typically grown on graphite or silicon carbide support. And so with reactive-FF, we could establish how the graphite edge structure can guide the growth. So we found out if the graphene essentially has these zigzag edges, then we get very strong local binding of gallium, but that's pretty much it. And the rest of the gallium pretty much organizes itself into sort of a spherical configuration, which is not desirable from a synthesis perspective. However, if we get the graphene to organize itself in armchair edges, we actually get the desired two-dimensional growth. So we see very much that the morphology of the graphene has a very important influence on the growth patterns of the gallium here. Also, what's interesting, so one way that they try to grow these type of 2D metals is they try to force them to grow subsurface, or to grow underneath the graphene, and they do that by essentially making these type of they use oxygen radicals to make the defects into the graphene, and then the idea is that the gallium precursors, which are pretty much a trimethyl gallium or similar type sort of organometallic, migrate through the holes and then dissociates in the subsurface and makes the gallium. Now, it turns out that in principle that synthesis works, but reality is a lot more complex, because it turns out that these trimethyl gallium species can actually also react with these edges and then partially heal these edges. So sometimes indeed you need to make very substantially large edge defects in the graphene to make this work. If your defects are too small, we indeed see that the defects kind of heal themselves during the gallium metal growth, and eventually indeed the gallium deposition may stop because there's essentially no defects left on the surface. So Skip is going to 2D, 3D materials for a second. And sort of a recent capability that we've developed is to run reactive-FF for ferroelectric materials. So we developed reactive-FF for these barium titanate materials. That we can indeed demonstrate that we see the transition from a ferroelectric material to a cubic transition at roughly 300 Kelvin. And then with these concepts, you can then, for example, look at thickness effects. So we see that for very small samples that the ferroelectricity disappears. And we see that there's a critical thickness that the material needs to have to allow it to have a ferroelectric transition. And we can also connect it to synthesis. So we work together with Clive Randall group at Penn State, who use supercritical water systems to essentially dissolve and reprecipitate materials. This is called cold sintering, where essentially can densify the materials at much lower temperature than using regular sintering, and creating a very high quality material at a much lower temperature with a much lower energy cost. Another important thing is that we can look at how surface chemistry can affect domain wall formation. And so here, for example, we stimulate how water reactions on the barium titanate surface affect essentially the migration of domain walls and as such affect the ferroelectric response. And so that feedback between surface chemistry and domain wall motion is pretty unique for a reactive-FF simulation. So we can take these things to higher temperature, and we can, for example, this goes back to batteries. We looked at LETP. This is essentially a battery solid electrolyte, lithium, aluminium, titanium phosphate. And we found out at elevated temperatures, and this is also known in batteries, during the battery cycles, eventually these electrolytes phase segregate into alumina and titania. And we could indeed do that simulation with reactive-FF. If you expose LETP to a supercritical water, we indeed see that we see these sort of phosphate chains dissolving from the surface. So we indeed see that phosphate leaves, and after the phosphate leaves, the LETP reorganizes itself into alumina and titanium dioxide. So that's indeed confirmed by experimental observation. Okay, so that hopefully gives you some sort of idea of some reactive-FF application. And I want to end my presentation by showing some new capability of reactive-FF and some new method development, where we extend reactive-FF with a limited explicit electron. So reactive-FF has charges, but it doesn't have any sort of explicit electron degrees of freedom. And that sometimes limits its ability, especially for simulating redox reactions. So what we do in e-ReaxFF, essentially we add an electron particle. So here's this sort of blue translucent particle, and that particle essentially changes the number of valence electrons for its atom host. So carbon normally has 4 valence electrons, and in reactive-FF that's essentially fixed. It doesn't matter what the charge of carbon is; it will always have a valency of 3. But in e-ReaxFF, if carbon picks up an additional electron or loses an electron, its valency will go back to 3. So it essentially becomes a carbocation or carbon anion, and that kind of changes its chemistry. One important thing that we can get right, so reactive-F doesn't really do very well for electron affinity. For example, reactive-F believes that CH4, methane, has a positive electron affinity, meaning that CH4 minus, according to reactive-F, is more stable than neutral CH4. But that's incorrect. CH4 has a very, very negative electron affinity. It essentially will not want to absorb electrons, because if it absorbs an electron, it has to break a CH bond, because the carbon goes to a valency of 3. And so e-ReaxFF reproduces that quite well. Similarly for water, so water has a negative electron affinity. reactive predicts it to be slightly positive, but OH on the other hand has a hugely positive electron affinity because the OH anion is much more stable than the OH radical. And e-ReaxFF describes that difference between water and OH quite well. So what we can then do is, one of the first things we apply these things to is for electron migration polymers. So we have here a polymer with an aliphatic domain and a conjugated domain and an aliphatic domain here in the middle. And then on the right side is a radical. And we see then it takes a little bit of time for the electron to get enough kinetic energy. Eventually it travels across and finds essentially the radical. But essentially the longer the aliphatic domain is, the longer it takes for the electron to be able to move across the aliphatic side. And so this is indeed something that we can directly compare with time-dependent DFT calculation and find out indeed that the time scales for reactive can be trained to essentially correctly reproduce these type of dynamics. Here's a nice example. This is an electron in water. So the electron is a translucent blue sphere we find in water. This is non-reactive. So the water molecules solvate the electron, but they don't absorb the electron because water has indeed a negative electron affinity. However, if I replace one of the water molecules with an OH radical, we see in a short amount of time, the electron finds the OH radical and makes an OH minus. So that's the green curve over here. And here indeed, after 2 picoseconds, we see the transition from OH radical to OH minus. That's exothermic. And but for the water molecule, there essentially is no chemical reaction happening. So this actually was a pretty nice and fast simulation. This took about 40 seconds on a regular laptop. And so we can relatively quickly include these relatively complex electron transfer into a REACT simulation. So one area where that is very important is for battery surface chemistry, where clearly electron transfers between the electrolyte and the graphite, for example, are very important. So here we have an example of an e-ReaxFF simulation where we have on top of where we have a lithium cation, we have a graphite with an excess electron. And we see indeed a e-ReaxFF can successfully describe the electron transfer between the graphene and the lithium plus. So this was the work done by Jamil Hossein. He graduated from my research group last year. And so he trained e-ReaxFF against a pretty substantial training set, electron affinities for a wide range of polyaromatic hydrocarbons. We also took aboard equation of states for graphite, so reactive knew the elastic response, and also values for electron conductivity. So reactive predicts that in the plane, the energy barrier for electron conductivity is only 1.5 kcal, and out of plane roughly 6.5 kcal. And so with that, we can indeed simulate, this is a simulation where we add an extra electron. So the extra electron is completely indistinguishable from the other electrons. I just made it red here to indicate it's the excess electron. We see that it moves very, very fast for the graphene. And indeed, if you take the time-dependent picture of that simulation, you see that the excess electron in red evenly spreads itself over the graphene system, which is what we indeed expect it to do. If we actually look at graphite, we see indeed that the electron only really transfer in the AB plane, and it doesn't transfer between the planes. So we indeed see high thermal electron conductivity in the plane and very low electron conductivity between the planes, which is indeed what we intuitively expect to happen. Now, if you add defects, we indeed see that the electron core sort of organizes itself around the defect. So around the defect, we have a higher electron concentration than away, and this is indeed confirmed by DFT calculations. And we can do sort of fancy things where we, for example, add sp3 linkers between graphene sheets, and we see that these linkers essentially play a role as a sort of a conductor for the electron. So now that we have these sp3 linkers, even though they have a lower electron conductivity than in plane, still they help the electrons move between the planes. So with that, we can indeed begin to simulate real sort of electron transfer at interfaces. And we can also look at, for example, transition between lithium plus to lithium metals. So if we, for example, add a couple of lithium plus cations on a graphene surface and we add some extra electrons in the graphene sheet, then we see indeed that those electrons move to lithium, they neutralize the lithium, so lithium plus goes lithium neutral, and then those neutral lithium atoms can essentially begin to plate and make a local lithium metal on the surface. So we can really do that transition between lithium plus and lithium metal, which is very, very difficult to do with other methods. So we recently managed to extend these to metals as well. So this is some force field development for iridium metal. So this is pretty much our traditional force field training, where we take various metal structures like FCC, BCC, simple cubics, and we train reactive-F to reproduce the energy difference and their energy versus volume behavior. But also now we put in their ionization energies and work functions. And so reactive-F correctly describes that, for example, an iridium atom has a much higher ionization energy than an iridium-28 cluster. And so this is indeed confirmed by experiment, where the iridium atom has the highest electron ionization energy, much higher than essentially the iridium metal surface. So now we can actually train these force fields to simulate electron transfer in the metal. So we can, for example, drive the electrons are here depicted by these translucent blue spheres, and we can drive the electron, for example, for the electron hole from an edge side to a central side. And we see that at very low barriers, you can move the electrons around. See, this is in kcal per mole, so okay. We see that at very, very low barrier, we can move the electrons around. The electrons prefer, the electron hole prefers to be essentially on the central side, but with a relatively low barrier, you can move it to the edge side. And so with that, we begin to open opportunities to simulate real electrocatalysis. So we can, for example, this is an iridium-28 cluster. We have here a nitrogen atom bound to it. And this is done with a neutral cluster, but we can do similar simulations where we add excess electrons to the iridium cluster and see how those electrons kind of affect the surface chemistry. Once again, this is a very fast simulation. This is 29 atoms with 29 explicit electrons. And this entire simulation took about 18 seconds of CPU time. This scale is actually very linear, so we can increase the system size quite substantially if we want to simulate more complex catalytic events. So here's a very nice sort of final demo of this method. This is a simulation by Ben Evangelisti. He graduated last year from my group. Here we actually bombard a series of parallel metal sheets with free electrons from the top. And we see that the first layer absorbs the electrons, then gets saturated and starts to emit electrons itself. And then they move to the second layer. That second layer gets essentially saturated. And eventually the excess electrons move all the way to the last layer. And we can see this process, how a metal turns from an electron absorber into an electron emitter. But this was a bit of a larger simulation. This was roughly about 4,000 or 5,000 atoms. So this took about 1 day to run on 20 cores. But you can really start to simulate how electrons can react with metals and how they essentially can get emitted from these type of materials. So that brings me to the end of my presentation. I hope that this has demonstrated the capability of reactive-F. So we have a wide range of materials. In particular, I gave some examples for 2D material synthesis. That's been a very active topic in my group over the last couple of years. So reactive-F provides has a low computational cost compared to quantum, so we can easily take this beyond 1,000 atoms and significantly beyond that if you use parallel molecular dynamics. And indeed, people have been reporting on reactive-F applications to well above 1 million atoms or so. And then finally, I showed you a new concept, e-ReaxFF, where you essentially expand reactive-F with a limited electronic degree of freedom to allow essentially electron transfer, explicit electron transfer during events. Well, I thank you very much for your attention. I'll be very happy to take your questions.